All right, let's dive into something pretty wild. We're going to see how a tiny, seemingly harmless environment variable can literally kick off a full-blown cloud breach. This is a story all about escalation, hidden dangers, and a single critical mistake that was made over and over again in an AI coding agent.
And look, right up front, this quote from the security assessment just nails it. We're not just talking about some simple bug here. No, this is about a systemic failure of trust. Think about it. When an AI agent is acting for you, where do you even draw the line? Where are the security boundaries?
So, our story starts with the most immediate, in-your-face threat you can imagine. An attack that requires, well, nothing from the user. Literally zero interaction. We're talking about a super-critical vulnerability that just goes off. No clicks, no typing, nothing.
Okay, so this is vuln01. And yeah, it's a classic command injection, CWE 78 for those keeping score. But with a really modern twist. The way in, it's the terminal environment variable, which is a super common setting on Linux systems. And here's the really scary part. Once an attacker poisons that variable, the agent just runs the payload, all by itself.
So how does this actually happen? It's a 5-step chain of events, like dominoes falling. First, a deep link handler gets triggered. Think of it like a special URL that opens an app. That calls a function to pop open a terminal. Step 3, the terminal reads that poisoned environment variable we talked about. Then a utility tries to figure out the path of that variable. And finally, a library called execa runs the command, and this is the kicker, with a fatally dangerous flag.
And right here, this is the smoking gun. It's exec with the shell true option. What this does is it basically tells the program, hey, don't just run this command. I want you to give this entire string to the system shell and let it figure it out. And of course, the command variable with our poison input is never cleaned up, never sanitized. It's just a wide open backdoor to run whatever code an attacker wants.
So you might be thinking, does this actually work in the real world? Oh yeah, the researchers threw everything at it. And as you can see from this table, it didn't matter what technique they used, command chaining with a semicolon, different kinds of command substitution. The shell just gobbled it up and ran the malicious command. This isn't some abstract theory. It's a 100% confirmed practical exploit.
All right, so that's the loud and fast attack, the smash and grab. But what if the attacker is playing the long game? What if their goal isn't just to pop a shell on a local machine? What if they want to be sneakier, more insidious? Well, that brings us to part 2 of our story, the silent supply chain breach.
I mean, what if the attack was designed from the ground up to be silent, targeting the absolute heart of a company's development pipeline? We're not talking about a single developer's laptop anymore. We're talking about the CICD system, the automated engine that builds, tests, and pushes out all your code.
And that brings us to vuln03. Now this one uses a totally different way in, a different vector. But as you're about to see, it's the same old flaw under the hood. Here, the injection happens in a configuration file. An attacker can sneak in a custom command, something called an API helper, that the agent is built to trust and run to fetch credentials. And that trust, it gets completely fatally abused.
So to prove this was possible, the first test was super simple. The question was, can a malicious API key helper just create a file on the system? The payload was basically echo fake token touch/tmp/marker. And yup, sure enough, that little marker file popped right into existence. That was all the proof they needed that the shell was seeing that semicolon and running the second command. But this is where it gets really clever. The next step was all about making the attack invisible. So they changed the payload to spit out something that looked like a real API key. The agent would grab it, try to use it, and then fail authentication. But here's the thing, it didn't matter. By the time the error showed up, the real malicious command had already run in the background. The attack works even when it looks like it failed. So sneaky. And here, this is the nail in the coffin, the definitive proof. They upgraded the payload to use curl to phone home and send data to an attacker's server. And what you're seeing here are the actual logs from that server. It shows that not only can an attacker run commands, they can steal your data. That first post is just it saying, hello, I'm here. And the next few? That's it sending chunks of a stolen file right over the network. And this is what turns this from a serious problem into an absolute catastrophe in a CI/CD pipeline. See, these automated tools run in non-interactive mode. For this agent, you just use the -p flag. And get this, the vendor actually confirmed this flag is designed to skip the security pop-up that would normally ask a human, hey, are you sure you trust this? The one and only safeguard is turned off on purpose. Okay, so let's recap. We've got 2 completely different ways to attack this thing, right? One uses an environment variable, the other uses a config file. They
They seem totally separate, but when you put them side by side, you realize they're just two sides of the very same coin. They both come from the exact same mistake.
Just look at them next to each other. Vuln01, that's the fast attack. It hits a local workstation through an environment variable. Zero interaction needed. Vuln03 is the more advanced, stealthy attack. It goes after the CICD pipeline using a config file, and its goal is to steal cloud credentials. So yeah, different vectors, different contexts, but the way they work under the hood feels suspiciously, almost identically the same. And here it is, the big reveal. This is the root cause. In two totally separate parts of the code, which.ts and auth.ts, you see the exact same vulnerable pattern. It's execa with shell true being fed a raw, unsanitized string. It's a classic, textbook, copy-paste coding mistake, but one with absolutely devastating security consequences.
So, what happens when a flaw like this gets loose, not just on one person's computer, but in the cloud? We need to talk about the blast radius here, because when this hits an automated environment, the impact is, and I'm not exaggerating, truly catastrophic.
So what's really at stake here? Well, inside a CICD runner, that little agent has the keys to the entire kingdom. We're talking everything. Anthropic API keys for the AI models, AWS credentials giving access to all the cloud infrastructure, GitHub or GitLab tokens for the source code, deploy keys that can push malicious code to production, even NPM or PyPI tokens to poison the software supply chain. Everything.
So here's the entire attack, laid out step by step. It's almost a playbook. 1. An attacker just submits a pull request with that poison settings file. 2. The CI pipeline kicks in, sees that -p flag, and just automatically trusts the bad config, no questions asked. 3. The malicious helper command runs. 4. It grabs all the environment variables and secrets it can find and ships them off to the attacker. And 5. It's game over. The attacker now has the keys and can just waltz right into your cloud infrastructure and private code repositories.
And that really brings us right back to the main point of this whole thing. It's the same root cause, that one little line of code copied and pasted, but the context where it's exploited completely changes the blast radius. Which leaves us with one final massive question. What happens when the trust boundaries of an AI agent, a tool that we designed to have deep access to our systems, what happens when those boundaries just fail, especially at cloud scale? Well, I think this incident gives us a pretty clear and, honestly, a pretty sobering answer to that.